Welcome back to the second part of our bar out episodes, where we will be defining the profile of the part. Make sure you watch part 1 before watching this episode. Let's get started with today's Mazak Minute. Hi, I'm Zillich, part of the HEH technical team. In today's episode, we're going to cover part 2 of bar out, where we're going to be defining the profile shape of the part to be machined. If you look at the screen, you're going to see that patterns consist of straight and tapered lines, as well as concave, convex arcs. We also have the ability to have taper lines having an unknown start point or final point. This can be calculated out as long as we give it an angle of the taper. And then unknown points of a line that intersect or that are tangent to an arc can be calculated with a known arc center. As we machine in the bar out, we're going to define our shape from the front face going towards the chuck. In our part 1 episode, what we covered was the unit description, which is the blue section that you see on the screen. Then in the yellow part is our tool descriptions, which tools are being used, speeds and feeds, and what is the depth of cut, and what pattern are we using. And finally, what we're doing here now is we're going to be talking about the green section, the figure pattern. This is where the definition of the shape occurs. So in that green section, you'll see that the balloon number 1, it says pattern. In this, you'll see on the soft keys that there is line, taper, convex, concave, and center. S corner stands for start corner. There I can have either a radius or chamfer at the start of the segment. Start point and start point X, start point Z is the start point segment of our figure. FPTX, FPTZ is the final point segment. Number 5, finish corner slash the dollar sign. Here we have the ability to define a radius or chamfer at the end of this segment, as well as the dollar symbol is an undercut profile. If we did have a taper or a arc, the R slash or hyphen theta is going to be the define the radius of an arc or define the taper line. Roughness, this is going to be the surface finish or feed rate of the finish tool for that given segment. So I put together a screen that basically is going to show the figure patterns for each one. The soft keys, when you're doing the selection, you'll see across you'll see line, taper, and you'll get a symbol for a convex arc, and then you get a concave arc. You skip a soft key, and then if I had an unknown dimension in an arc, we would then need to put a center after the arc. In the green symbols or in the green windows below, you're going to see that each segment, some of the fields have a diamond in there. Those diamond fields can't have a data put into them, and as you cursor through, it will skip over each one. So in a line, start point is a diamond out. You only need to put the finish point. On a taper, all the fields are available, as well as for the convex concave arc. When you get down to the bottom one, the center, you'll notice that there is no start corner, but there's a start point X, start point Z, and that's going to be where we define the arc center. If we look at each one individually, here you see the line, and the first part that comes up is that S corner. I brought in a drawing from one of our class books, and what I want to point out here, in this line, I would be programming this start corner, to be a 60 thousandths chamfer. If you notice at the prompt window right here, it says start corner C, or it says corner R, hit the menu. So if I want to put a chamfer in, I can just type in the 0.06, but if I want it to be a radius, I would come over here to the left soft key where it says corner R, highlight that first, and then enter in the 0.06, and you'll notice that then in that window or in that field, it's going to say R.06. On a taper line, you have the ability here to have start point X, start point Z. Because there's a beginning and an end to it, it could be at two different diameters or two different positions in Z. We're going to come here, if I move my cursor there, notice the soft keys down below. It's going to say question mark, and that's basically our unknown. It's going to be for an intersect point as well as continuous point, which would be like it being tangent. If you hit the question mark at the top of the screen on a smooth G control or EZ control, or I guess on the EZ control, you're going to hit your far right menu key, the far right soft key, and then or arrow key, and then you're going to press the help soft key. That will get you the window down below. The nice thing about the window down below, you're going to see the start point is going to be over here at the beginning or at the end of the straight line, and then you'll see the end point. It goes up to X2, Z2, and the chart to the right, you'll notice that it's showing you where I can have a question mark in. If I have a question mark in one of those fields, we will have to put the angle under the radius theta column. In the back of the programming manual, there's a chart here that I like to show people in my classes. It's going to show you when to use a positive angle and when to use a negative angle. If we're doing a bar out, I always tell people as it's cutting, if I take less stock as it goes up the shoulder, that would be a positive angle. If as it's cutting and you're going to dive down or get smaller on the diameter, taking more stock, think of that as being negative. An example that they have in the book, here we have a taper. They have their numbers in metric, but if I look down below here, we have a figure pattern line, the two diamonds, and then we have a 30 millimeter diameter going back 20 millimeters. We go down to the second figure pattern. We have a taper. And when you have a taper with a known point, you're going to see probably when you have the cursor over here by S corner, there will be a soft key that says next. And what that next will do is it will bring down the previous finish point X and Z and put it in the start point of your taper. Then on the end of the taper, the finish point X, finish point Z, we do know up here that we are at 50 millimeters. However, I don't know the finish point Z, so I would hit the intersect question mark on the soft keys. Come over to the R theta column, and where we see that 30 degrees, again, it's a positive angle this time, so we'll put positive 30 in there. What I'd like you to do now, if you would, go ahead and pause the recording and take a picture of the screenshot. What we're going to be doing now is I'm going to switch over to our SmoothCam software, and we're actually going to go ahead and program this part together. So now here I am. Basically, I have a program open. I already took care of creating the unit, the tooling, and what we're going to do now is I'm going to actually go ahead and I'm going to go ahead and clear that out so we start from scratch. And here, figure pattern 1, if we look at the drawing, I'm going to have a line. And myself, I'm not a big fan of deburring parts. So even if the print doesn't call for it dimensionally, sometimes if you look in the title block, they might say that you have to chamfer all sharp edges by maybe 10 or 20 thousandths. So in my case here, what I'm going to do is I'm going to go ahead and put a 10 thousandths chamfer. I'm going to come down here. You notice in the prompt box, it's asking me for start corner C. I'm simply going to type in 10 thousandths. Diamonds for the start point. I only need to define the finish point of the X and Z. So this is the X is a diametral value. So I'm going to go ahead and type in 2 inches. The Z is going back 1.75. I don't have a finished corner in the end, but if I come over here to the roughness, if I leave the roughness blank, it will go by the finish tool here of that 10 thousandths per rev. The only time it's necessary to change the roughness per segment is going to be maybe you have different micro finishes. Maybe there's most of it is maybe 125 micro, and maybe there's only one section that's 63. I can change the finishes per segment in this area under RGH. RGH, if you see it, it says surface finish feed rate. I'm going to go ahead and come down to the next line or next figure, and now I'm going to go ahead and do the taper. Okay, on the print you'll see that yes, we do have both the start point and finish point, but you notice that there are 2 placed decimal points. 2 placed decimal points, typically the tolerance is pretty open on them. So what I plan to do here is I'm going to go ahead here, hit the taper, and then I was talking earlier that if I want to bring the finish point from the previous figure, I can come down here on my soft key and hit next. Notice that the 2 inch and 1.75 come in. I'm going to go ahead, type in the 4 inch. But this time I'm going to come down. I'm going to let the machine calculate out the finish point Z. We're going to come down here to intersect point, question mark. Okay. And then I'm going to come over here to the R theta column. And because this is a taper, notice that my prompt box is asking for the tapered angle. I'm going to go ahead and type in 30 degrees. And what I can do is if I wanted to see the number get calculated out immediately, I'm going to come over here, hit my right arrow key, and then over towards the left on the soft keys, there's a soft key called calculate. And if you notice now, we have a Z value of 3.482. Okay, it's quite a bit different. Oh, you know what? I made a mistake, and I just caught it myself. I made it 30 degrees from what our previous example was. So if I look at my print, I notice a big difference. So I'm going to go back and put the question mark in there. And if I would read my print and look at the print, I see that that angle is 26.57 degrees. Now I'm going to come back, go ahead and hit the calculate. And now you can see that the dimension is 3.74957. Again, if you look at your print, you see how it was 3.75. I now know that I'm accurately at that 26.57 degrees. The last figure I need to define is going to be the horizontal line. And this is going to be, if I come over here, I'm going to say line 4 inches, going back to 4.75. Now the one thing I don't have to do is if I'm doing a bar out, I don't need to define the vertical lines. That will automatically cut back up to the 5 inch of the contact point X. If we go ahead, and I'm going to go ahead and put an end statement on here. I'm going to say shape end, end. And what we're going to do is let's go look at it in the tool path. We're going to come over here. I'm going to hit the far right, program complete, and do a tool path. And I'm going to come here and do a part shape. Notice you see the profiles. If I would zoom in pretty close, you could see a chamfer on there. But if I go ahead and do a path step, you'll see I am cutting that profile. Now, just for an example, maybe there's a radius at the end of the line. If I come over here to my finish corner, program edit, and I come over here to radius, I'm going to go ahead and type in a big radius so that we can see it. I'm going to say 1.5. Okay. Now when I come back to my program toolpath, part shape, Notice you got a big radius in there now. So if I go in here and I do the path step, as it does its motion, you get that radius in there now. So the nice thing about Mazak is that if there's an engineering change, there's a print change, a revision, if it's something to do with the radius, all I need to do is come back into the program and change that one number, and I'm ready to machine. Let's go back into our PowerPoint presentation. And what we're going to do now is we're going to go into talking about creating an arc. Okay? When you go to an arc, you're going to have your figure pattern line. It's going to be convex or concave. In the example what they show here, we're doing a convex. Start point, or the S corner, is going to be the radius at the beginning. Start point is going to be the point at the start of the radius. Finish point X and Z is going to be the end point. And again, the R theta is this time will be the radius of the arc. So example that they have in the book, here we have a line to an arc to a line. So they're actually starting with the arc itself. So we're starting at a 30 millimeter diameter. And notice how we don't know the z-axis. So we're going to go ahead and we're going to say z question mark with an intersect. Then the end point of the arc, I don't know the x dimension. So down here I have a question mark for the final point x, intersect type. But I do know that from the datum point, I'm 60 millimeters in. But as soon as you have an unknown point, the question marks in the arc, the next unit or the next figure pattern needs to be the center, which for the start point and for the x and z, the x will be the diametral value of the start point. And the z will be the from the datum back to the arc center. So here you're seeing a 10 millimeter diameter by 40. The definition on the screen below is exactly what I was talking about, that you must hit the center once you have a question mark. The next example, there's times where maybe your arc center may not be inside the part or above center line. This is a perfect example where here you're seeing that the arc center is 10 millimeters in front of the part, as well as 20 millimeters diametrically below center line. If we look at the figure pattern down below, we look at the figure 2, notice that the start point X is negative 20 and the start point Z is minus 10. In there, once you have question marks as well, there may be times that you need to define a modifier. Modifiers on that center line, or that figure 2, at the beginning for the start point will be under the R theta. There will be soft keys that say up, down, left, right. And then for the final point, that would be underneath the rough column. And again, it would be left, right, up, down. And I guess the best way to explain it is if you have that circle going around here, okay, that being at a 40 millimeter radius, it can actually have two possibilities of intersecting on that 40 millimeter diameter line. It's going to be the, you're going to make the decision between the two possibilities. So if I have a possibility here, this would be left of this opposite one over here. Likewise, if I wanted the one on this right side, I would select right. Most people make the common mistake thinking of it as the relationship to the arc center of the circle or the radius. It is the relationship between the two possibilities. And we'll get into that in a few examples. The screen here, if you take a time to look through it, you're going to see exactly what I said. Underneath R theta, you're going to have the up, down, left, right for your start point, and roughness, you're going to have it for your finish point. Here's another example here where they're using at the start point. They have an arc starting here, and this time we know the value of X is 50 millimeters. We put a intersect question mark for the Z. We know the finish arc is going to finish at 40 millimeters, and the Z is going to end up at 47.321 with a radius of 20. Again, because we have an unknown question mark, the next figure pattern is going to be a center. Start point X, start point Z is going to be the arc center. Both of the values are positive. We are above center line and in the parts. And then this time, the question mark is on the start point. So you're seeing under the R theta is where we're going to put our modifier. You see how they have them specified as A and B? Well, in this case, I want the line to stop here and come all the way over to the finish point. If I chose the other point, if I chose a left, it would have cut this line straight across and only given me this small section of an arc. So as we wanted the A, you'll notice down below here, they chose right. Once you have that center point, if you want to go ahead and calculate it, you can go ahead and hit that far right arrow key and then go ahead and hit calculate. So again, what I'd like us to do is let's go ahead and pause the screen. Take a picture if you would with your cell phone, or if you want to do a screenshot with your computer. We're going to go ahead and program this part together. This is one of our class examples that we do in our classes here at Mazak. I'm going to go ahead and bring back the smooth cam. And this time, let's go ahead and I'm going to change my prints over here. I made a copy of it for myself. I'm going to come across the top. In our common unit 0, I got carbon steel, 5-inch diameter. In this case, the part length is going to be 7 inches. And for the example, so that I can go right to the bar out, I'm going to say that my work face is 0, that basically I'm not going to face the part. You're going to see that I have it grayed out here right now. I come down below to my bar out, my contact point, and earlier I was talking about the contact point. If I hit the question mark, you'll see that the contact point is going to be where I come into contact from the tool coming down from the tool change position. Hit your question mark again to turn it off. In this case, I have 5-inch stock starting at 0. I'm going to go ahead and accept those tools. And what I'm going to do now is I'm going to go ahead and erase out the figure pattern and the end statement. So I'm going to come here and say erase, and I'm going to cursor down and hit the end. And on a smooth G control or a smooth AI control, as well as a smooth EZ, we have the ability to erase multiple lines at one time. I cursor down now and I have a blank figure. So I'm going to come here and I'm going to do a line. I'm going to put a chamfer of maybe 20 thousandths this time. We're going to go at 2.375 diameter, cutting back 3 inches. The next thing I like to do is I can come here and I'm going to do a convex arc. Okay, I like to work smarter, not harder. So what I'm going to do is I'm actually going to come here and hit next, and notice how it brings down the previous point. So this captures my z-axis for me. I know my x-axis is wrong, so I'm going to come back to my start point x, and I'm going to go ahead and say that this is a intersect point. My finish point, I'm going to come over here. Finish point X is going to be 5 inches. And finish point Z is going to be 4.73. If I come over here to, now notice that my question mark is over here on the start point. The last thing I need to do on this convex arc is come over here to R theta. I'm jumping the gun. I'm getting ready to talk to you guys about the center, but the last thing I forgot to do here is going to be the radius. The radius of the arc is 2 inches. Come down to the next figure pattern. This is what I was leading into. We're going to come here. We're going to do a center. The center point of the arc, if you look at that print, it's showing me that there's a 2-inch radius that I'm machining, but it doesn't give me the arc center. Well, there's 2 ways I can get that arc center. The first way is I'm going to double that radius, that 2 inches, so that gets me 4, and then I'm going to subtract it by the large diameter. So 5 minus 4 will be a 1-inch diameter. The other method that you could do is if you take that 5-inch, divide that in half, that gets me 2.5, and then 2.5 minus the radius, 2-inch, that gets me a 1/2 inch, and then double that because we have to program the arc center as a diametral value. That still gets me that 1 inch. The Z value, that is on the print, that's going to be that 4.73. And then when we come to the modifier again, or the question mark, was on the start point. So under this R theta column, okay, I have up, down, left, and right. So if you would draw a complete circle around the arc center, you'll notice that that arc will intersect that 3-inch Z position 2 different places. I want to go ahead and choose the up. Now if I go ahead and go to do a toolpath, or actually I can do a toolpath, or I can hit the far right arrow key and do a calculate. And you'll notice that the number where I had the question mark got filled in. I'm going to go ahead and do a shape end. So I click on the pattern for 4. There's a shape end soft key down here to the right. And now when I come here and put an end statement, I can come over, do a program complete, and do a toolpath. And when I do a part shape, notice you can see that that circle is actually intersecting with the line. So the whole reason I couldn't do a start corner on this is because that radius intersects the line. It's not tangent to both surfaces. I'm going to go ahead and let's go back to our screen. And now what we're going to talk about now is going to be in our figure patterns. Notice the finish corner $. The finish corner $, yes, I could put the radius, the corner radius or chamfer, using this corner R or just typing in the number. But for finished toolpaths, sometimes for areas that you have to grind, a lot of times they want to have an undercut. So Mazak has given us the ability to have $1 through $6. What I'd like to point out is that $1 looks the same as $4. $2 is the undercut on the face of the part, which looks like the same as $5. And finally, 3 and 6 look the same as well. The difference being is that 1, 2, and 3 use the same 2 parameters. So I like to refer to those as my default undercut. And then finally 4 would be the custom one of number 1, 5 is the custom of 2, 6 is the custom of 3. The parameters are going to be identified in parameters TC27 through TC34. On the next screenshot, what I have is the parameter for 1, 2, and 3. So if we look at number 1 here, TC27 is going to be the width in the Z-axis, where TC28 is the what I like to refer to as the depth in the X-axis. On the face of the part, again, TC27 is going to be the width. TC28 is going to be the depth in the Z-axis. And then TC28 is going to be, basically it's going to do a corner undercut, and it's going to do both. You can see TC27 and 28 have their values there. So as I said, that basically number 4 is the same as number 1, and it will look just like this picture right here, but it will now have TC29 being the width and TC30 being the depth of it next. But if you get a chance, take a look at your parameter books. Look at TC, what did I say, 27 through 34. Get a good understanding of it. Notice when I do change the values, it's going to be immediate. The program type, this is only effective for a Mazak program. And the values in the parameters that you change, in this case, it's going to be a 4-place decimal. So if I wanted 20 thousandths, I would put 200 in there. So the other important thing about the undercuts is that the tool that you're using needs to have the clearance to be able to machine the undercut. Notice that here in case 1, or in the type of 1 and 4, your A angle needs to be greater or equal to 93 degrees, and B, the included angle of the insert, needs to be less than or equal to 57 degrees. So a DNMG insert would be perfect for that. As well as A plus B needs to be less than or equal to 150 degrees. In the case of a 2 and a 5, notice that the A has to be greater than or equal to 120 degrees. So if you could picture your tool, that tool needs to be laying out a lot more so that I can do the undercut in the face. Finally, for the undercut for a 3 and 6, notice that the B is less than or equal to a 30 degrees. So even a VNMG insert won't be able to cut that for me. There are some tooling vendors out there that I believe have like a 22.5 degree insert that you can take a look and ask about that. The next item in the figure pattern is going to be the roughness. Okay, this is where I said earlier that if you had different micro finishes on different surfaces, what we have the ability to do is I can change either the roughness or the feed rates. The roughness is a way to, Mazak has a numbers 1 through 9 to identify from coarsest to finer finish, as well as you have the ability to use feed rate per rev. On the next screen, we're going to go ahead and look at the roughness. And like I said earlier, we're going to have 1 through 9. You look at your finish, and basically you're looking at micrometers. So you have 100 micrometer, 50, 25, 12.5, 6.3, 32, 6, or 1.6, 0.8, 0.4. So the higher the number, or the finer, the more numbers of arrows you have for finish markers, the finer the finish. As I tell people in class, if I'm using a micro finish an inch, I'm going to say that this is going to be a 1,000, 500, 250, 125, 63, 32, 16, 8, and 4. Granted, I'm not going to turn an 8 or a 4, but just keep in mind that the higher the number, the finer the finish. I've had luck where that 4 and 5, I have seen that 125, 63 without a problem. If I come down to the next, is going to be the feed rate per rev. The feed rate per rev, I use a little bit more myself. Tooling vendors, they have charts that basically they'll tell me what the tool nose radius is, and then a chart at the top that maybe shows me the micro finish. And if I do the cross section, it would tell me the inches per rev to type in. If you had one line segment that had broken up into maybe multiple micro finishes, you can program each, even though it has the same X, I can program the Z surface at different ones, and go ahead and put in a different micro finish for those sections. Lastly, just as a precaution, when you're doing a bar out in the box, remember that's the ones that start in the middle, or in this case you see how they're cutting from the front and then they're coming down. Well, the Mazak is actually monitoring the front and back edges from the description from the tool data page. So on the front side of the tool, if we look here in the section, I have an A degree, which is my lead angle. And notice if I'm coming up that shoulder, if that was more of like a neutral tool, you're going to see that A minus 3 degrees, so it's going to give me some clearance there. On the back side of the tool, you see the C degrees, and again, it's not going to allow me to rub the back edge of the insert as I'm cutting. Thank you for watching. I hope this helped you define the profile shape of a part. Now you can come back and reference these episodes as many times as you'd like. Leave your questions in the comments and be sure to like the video and subscribe to the channel. Thanks, and we'll see you next time on the Mazak Minute.